Hello everyone, this is video 6 of chapter 4 of the lecture notes. In this chapter we've introduced the notion of cyclic groups, and in the previous video we saw how to build a trapdoor function using cyclic groups, which we call the discrete logarithm problem. Now in this video we're finally going to see how to use this trapdoor function to build a public key cryptosystem, namely the Elgamal cryptosystem. So the whole information about this crypto system is captured in the box that I'm sharing with you right now, that is taken from the lecture notes. And if you're able to understand all the details of this little box, then you've understood everything about the Elgamal crypto system. But before we go into the details of this, let me just discuss the broad picture of how this works, what are the different information that you have to handle, and so on. Okay, so to have this broad picture, I'm separating the information in three pieces. Okay, so in the general situation, we always have two agents, A and B, that are exchanging information. And in public key crypto system, there are information that are secret and only known to A, information that are secret and only known to B, and public information that are known to both A and B, but also to any enemy that might intercept the message. Okay, so when we're doing this, the first thing that is known to everyone is that they are using the Elgamal crypto system. So this is public, okay? It would be public as well if they were using the RSA crypto system. People need to be to know which crypto system they are using, which method they are using. In the Elgamal crypto system, the first thing that is public is which is the public domain you're working with, and the public domain, as we will see in a second, is the choice of a group, a cyclic group, and the choice of a generator, okay? So everyone knows that A and B have agreed to work in the framework of a certain group with a certain generator, okay? Another thing that is, of course, public in any public key crypto systems are the public keys, right? EA and EB, which are public, and they are the enciphering keys, right? So this works as for RSA, the enciphering keys. So they capture the information that are needed to send a ciphered message, EA to send a ciphered message to A, and EB to send a ciphered message to B, right? The private information that is secret and only known to A is DA on the one hand, which is the deciphering key. So A should be the only one knowing how to decipher the messages she receives, the ciphering key, and the same is true for B, of course, DB here, the ciphering key. Okay? Now suppose we're sending a message. Suppose we are in the situation in which we're sending a message from A to B. Okay? So which information is used in this case? When A is sending the message to B, of course, she needs to use the enciphering key of B. Okay? So this is part of the things that are used in this process of sending a message from A to B. What is new in the Elgamal crypto system compared to the RSA crypto system is that A is also going to generate a disposable key that is only used for this single message. Okay, so I'm going to put it here. It's going to use something that we're going to call key, a K, which is a disposable private key. Disposable private key, which is used to encipher the message, okay? And at the same time, it publishes a disposable public key, only for the sake of that message. Disposable public key. Public key that we're going to call R. And this is also used by B to decipher the message, okay? So whenever a message is sent from A to B, well, there are four informations that are used. B is also, of course, going to use its deciphering key, okay? So these are the four informations that are used whenever a message is sent from A to B. Now let us look at the details of how this works. So I've already told you the first step. The first step is that A and B need to agree on a public domain, on a framework in which they're going to work, okay? So this public domain is the choice of a cyclic group, okay? So any cyclic group that you know in which the discrete logarithm problem is hard. So for example, z over nz with multiplication and taking the 0 out, and the generator G, little g. Okay, so that's the public domain. Second one is how do we generate the public and private keys. Okay, so generation of the enciphering and deciphering keys. Deciphering key, which is secret, right? And the enciphering key, which is public. All right, so it will always follow the same pattern. The ciphering keys or secret keys are always going to be numbers. It's just a number. It's a number that is secret, chosen randomly between 0 and whatever huge number you want to choose, and it's only known to you, that number that you have chosen. Okay? The enciphering key is going to be an element of G, of the group. And how do you build this element? Well, simply take EA to be equal to G, the generator you have chosen, to the power of the number you have chosen. Okay, so that's how you generate an enciphering key. Okay, and of course, what is important is that this relation between the public and private key is actually better to think it the other way around. So how do you know what is the secret key equal to? So it's equal to the discrete logarithm of the public key. Okay, and this relation here shows that to protect the secrecy of the private key, it's important that you cannot compute the discrete logarithm. Okay, so the fact that you cannot solve the discrete logarithm problem is the key point in the security of the Elgamal crypto system. Okay, of course I'm saying this for A, but for B you also have to create enciphering and deciphering keys, right? Okay, which of course you can also write as EB is equal to G to the power DB. Okay, so then now that we have this, I can tell you second part, how to encipher a message. And let's suppose enciphering of a message that we send, let's suppose we send this message from A to B, okay? From A to B. All right, so the novelty here that it was not existent in the RSA crypto system is that you start by generation of disposable key. So it's a key that you're only going to use for this single message. Disposable key, okay? So we call it K, and it's a number, again, a number that is randomly chosen, and we call it K, right? And therefore there's also a public key that you generate at the same time, a public key, which again is written in the same way. R is J to the power K, okay? So the private keys are always numbers and the public keys are always elements, right, of the group. Okay, this information is published, R, and now that you have this, I can tell you what the enciphering transformation is. So the enciphering transformation is going to depend on the number you have chosen, which is secret, but also on the enciphering key of the person you're sending the message to, which is EB. Okay, so that's a transformation that goes from G to G, and if the plain message is X, the enciphering transformation gives you a ciphertext, which is Y, and it's very simple. You just do X, and you compose it by the element that is the enciphering key to the power that you have chosen. Okay, so that's the enciphering transformation. And the information that is received by B, information received by B, is twofold. on the one hand, it receives the disposable public key R, right? And it also receives the cipher message Y. Okay, so there are two things that are received. This is the cipher text, and this is the disposable public key. All right. Okay, and the last thing that we need to understand how it works to have everything about the Elgamal cryptosystem is the opposite transformation, so how to decipher a message. Deciphering transformation. Deciphering. So deciphering by B, right? B is the one deciphering a message. So the first thing is that B receives the message RY, right? Receives the message RY, so that's an R. And to decipher, well, it's a transformation decipher that depends only on the deciphering key, DB, that goes from G to G, and it goes in the opposite direction of the enciphering key, right? So you receive the ciphertext and you transform it into the plain text X. And what's the operation that you do? Well, X is in fact equal to Y composed by R to the power DB minus 1. Okay? So let's box this because this relation is quite important. And that's everything about the Elgamal cryptosystem. Perhaps the last thing is just to convince you that indeed it's true that X is equal to this expression here. So if you remember that the definition of Y was that it's equal to X composed by EB to the power K, and you also remember that R is equal to G to the power K, and the last definition is that EB is equal to G to the power DB, and you combine everything together, then you'll see that this expression gives X, well, the expression that we just wanted to compute here, this expression Y composed by R to the power DB minus 1, let's see what it gives. So you just plug X composed by EB, I replace it by G to the power DB, right? The whole thing to the power K, okay? And then I apply composed by R, but R is J to the power K, and the whole thing to the power DB, and then the whole thing to the power minus 1. And you can notice that these two expressions are the same. G to the power DB to the power K and G to the power K to the power DB are the same. So in fact, these two elements are opposite, are inverse to each other. So this part here is equal to the identity E. And therefore, it is true that this operation gives X. Okay?